Okay, my presentation covers the first part of clinic trial, which is in the pre-formulation and formulation. As you have seen the slides probably over and over again, my emphasis is on the first part, which include drug characterization, basic formulation, and some advanced drug delivery systems. Let's first look at the pre-formulation, which is drug characterization. So what is a pre-formulation? This is a phase of research or development that you actually characterize the physical chemical property of a new drug entity. And you're trying to figure out some basic information so you can move forward. Like Dr. Bennett mentioned earlier, pre-formulation sometimes is underestimated because we don't think it's quite relevant to the big clinic study. But actually, it's very important because it's not only provide insight to how the drug product should be handled and stored or scale up, but it also can provide very useful information to generate or design a drug delivery system, so actually they can carry it into an animal study in the future. So when we actually need to start the pre-formulation study is when you have a lead compound in your hand, which has been probably selected from millions of the library you have, and you found that that lead compound have a very interesting and sufficient pharmacologic promise in vitro or in vivo to treat certain disease that you wish to treat, and they require further PK/PD study. So the general route we need to start with pre-formulation is to establish some physical chemical parameters and to determine its kinetic and stability and to evaluate its compatibility with some common excipients. So in our CCPF core facility, we focus on those two areas of pre-formulation or drug characterization, which is stability analysis, solubility analysis, and stability evaluations. For stability, we normally look at dissociation constant, pH solubility profile, solubilization, partition coefficient, and dissolution. We recently acquired a new instrument called PION Ceres T3, which we just have a talk with some people from industry. This is a very current industry gold standard kind of instrument, which can give you all those solubility parameters with very detailed information like this reference shows. And for the stability evaluation, for the dissolution, we also recently acquired a new instrument called SOTAX Apparatus 4, which is capable of doing some of the dissolution on the nanoparticle formulation we have in hands. So for solubility analysis, which is always the first step, is trying to study the drug compound in some of the common pharmaceutical solvents and biorelevant buffers. And the first thing we need to do is develop either HPLC or LC-MS analytical method to actually be able to quantify the drug data in solutions. So we have HPLC and LC-MS instrument available to perform that, like Dr. Liang mentioned earlier. I want to give some general knowledge how we started the pre-formulation. We look at the Linsky rule of 5, which is basically if a compound with hydrogen bond donor less than 5, molecular weight less than 500 dots, log P less than 5, and H bond acceptor less than 10, we consider it's a good or it's worth going forward. It's a drug compound like that. This is a soluble level table, which shows how to characterize a drug into the different levels. Unfortunately, most of the drug that we're dealing with, which need a formulation is falling under the slightly soluble to insoluble range, which I mentioned later. Dissociation constant pKa is the acidic constant negative log of Ka. Normally, the higher the pKa, the weaker the acid, and vice versa. Partition coefficient defined as a concentration of drug in octanol phase over that concentration in water phase. So normally for log P, positive means lipophilic and negative means hydrophobic. Again, most of the drug we're dealing with is very lipophilic instead of hydrophilic. So this is an example I'm giving on one of the compound we have studied. We start to look at the Lipinski property of this compound. We look at the hydrogen bond donor acceptor, less than 5. Acidic pKa is 10.6, and basic pKa is 4.3, so this compound is more basic. Estimated log P and experimental log P is pretty much the same, 3.45-ish, and it's less than 5, and the molecular weight is less than 500. So this is an okay compound to move forward. We then studied the solubility at various time after 72 hours. As you can see, they're soluble in water as 0.46 milligram per ml, so it's considered as a very slightly soluble compound. But they do have some solubility in those organic solvents, which can generate information about how we can do a basic formulation later. And we also studied the pH solubility of the compound at lower acidic environment and neutral pH, and found it to be more soluble at acidic condition because it's more basic. So let's look at the stability evaluation, which is trying to see if very easy to understand, if a drug is stable over its shelf life, or how long it's stable, so how we can handle it while we're doing those analysis. So we normally use this instrument. We have a stability chamber, so they can do force degradation study, and they have some humidity and temperature control. So they doesn't have a fluctuation environment, and we can perform some specification exceeding the FDA requirement. So the condition change we'll look at including the temperature, of course, sometimes the pH, sometimes the light, if the compound is light sensitive, and also the length of time the freeze-thaw. And we have the HPLC or sometimes UV spectrometer to look at the compounds over time. So here has several examples of the different stability evaluation we performed on the compounds. We have done solid state stability of this compound B at different temperatures and up to a month. So we can see this compound is pretty stable even at room temperature. On the other hand, the compound C we just recently doing study with, they are not that stable, even up to several days at room temperature and accelerated conditions. So for those compounds, we need to pay more attention when we're doing the formulation and animal studies. pH stability of compound A, you can see they are most stable at the neutral pH, but the acidic environment, so maybe they undergo some of the degradation like hydrolysis. And for compound D, they're more stable up to 72 hours and at all of the pHs. So those information can help us further in the next step. We're going to talk about the basic formulation. So the reason we do basic formulation, like Dr. Brennan mentioned earlier, your formulation at the end might not be the formulation you start with. Sometimes it even change in phase 3. But the reason we do insolubility at early stage is you have to have a formulation to carry your drug into the animal study. if you have a perfect molecule, which is, class 1, then you probably dissolve in saline or water, then you can have a formulation, you can do the animal study. But unfortunately, most of our compounds are not in that perfect ideal situation. We have to have some solubility to make it druggable. So we start with some simple and non-toxic formulation to have a required solubility of the drug to start the initial PK, PD study into animal. And depend on the drug candidate's pre-formulation profile, we can add in oils, surfactant, co-solvent, complexation agent to increase the solubility. Sometimes suspension emulsions can also be developed to help that. The one we use most often is co-solvent. Again, it's because it's simple. And it can increase some of the poor water soluble drug significantly with just adding a little bit water and one or more other water miscible solvent. So here it shows some example of co-solvent formulation. So with this compound B, as we can see, it's pretty much insoluble with a solubility at 0.28 microgram per ml. So this is one of the very difficult compounds we'll work with. But they do have some solubility showing in some of the solvents as we start a bunch of them. So this helped us to develop a co-solvent formulation. We studied over 50 or 60 different combinations of different solvents, and finally here shows some of them. And we found one with PEG 400 and 280, which increased the solubility to 7.5 milligram per ml, so which is 26,000 times of the increase. And we studied the stability of that co-solvent formulation at different temperatures and found it's pretty stable up to 1 month, so we feel comfortable to use it. And the same study we did for another compound, which is have a little bit better solubility at 0.4 milligram per ml, but it's still too low for doing any animal study. So again, we use a solubility table we generate. We study combination of different co-solvent formulation, and we find the one use Labrosol and PEG 300 to get the concentration to 10 milligram per ml, which is 25 times increase. And we started solubility at several different temperatures and found at least they're very stable at 4 degrees, so we feel safe, comfortable to use those formulation at this temperature. Another complexation agent we use is cyclodextrin complex, which is a bucket-like molecule. They have the hydrophobic pocket, which can have the hydrophobic or lipophilic drug put inside, and they have a hydrophilic exterior outside, so it can be soluble in aqueous solution. And HP beta CD is the one used quite often for injectables. And we need high concentration of cyclodextrin to be able to be a solvent, be a formulation injectable, but they do have a problem if the concentration is too high, they will have some toxicity issue, which I will mention later. So this is the compound B, HP beta CD complex we formed with one of the compounds I mentioned earlier. They can increase the solubility over 10,000 times. So next step, I want to introduce advanced drug delivery systems. So with all the basic formulation we mentioned earlier, sometimes a basic formulation might not satisfy the requirement of the study we need. So because a basic formulation, like I said, is simple and it's easy, but they do drug release immediately, and sometimes it causes fluctuation of the drug level in the blood, and sometimes they have a limited concentration in the formulation, so you need large volume, etc. On the other hand, a lot of groups around the world study more advanced drug delivery system because they can improve the solubility even better. They can obtain better stability and less toxicity. They can maintain the drug concentration within the therapeutic range. We call that provide sustained release. They can achieve better targeting delivery with probably adding peptides or antibody on the surface of the nanoparticle, and they can enhance the PK profile of bioavailability. This figure adapted from the reference shows a different type of advanced delivery system, which is studying around the research fields. And the one we study most often is polymer-based micelles, Lipson and solid nanoparticle, and also gold nanoparticles. So I think everybody knows Lipsons. This is the scheme shows a different type of Lipson, which is basically lipid bilayers. You can put the water-soluble molecule in the center, and if you have a hydrophobic drug, it can be buried between the bilayers, and the outside is hydrophilic. And you can also add PEG to the surface to become Still's Lipson nanoparticles, so which can circulate longer in the blood. And you can, depend on your requirement, you can add in antibody or other targeting molecules to make it specific target, for example, to certain cancer tumor surface. Or you can add image to make this particle to be observed under with some specific imaging tools. So it's all dependent on what you are looking at. So this diagram shows a preparation of the Lipson drug delivery system. And in our lab, we have the rotary evaporator, which is basically at, I don't know which one, at this stage can show the, can make the dry lipid film. We also have the extruders and microfluidics, and as well as sonicator, which can make the multi-layer vehicle downsize to single-layer vehicles. And we have Marvin data sizer, which can characterize the particle in terms of their size and zeta potential and how uniform they are. Very quickly, we developed some compound B Lipson formulations with the combination we studied at different material and ratios. And we later add a PEG molecule on the surface to further increase the stability, the circulation of that Lipson nanoparticles. Here's a diagram of zeta sizer before and after exclusion. Not only the size decrease, the more important is the uniformity. So how the distribution of the particle is much more uniform after the exclusion. And we then performed PK study on the two Lipson formulation with comparison with the co-solvent formulation we did earlier. Although the Lipson formulation is only 1/10 of the dose of the co-solvent formulation, but you can see the PK profile is much better. So that is proof shows the advanced drug delivery system can increase the PK profile. Another nanoparticle we study very often in our lab is PLJ-based nanoparticle. PLJ, I think everybody knows, is a biodegradable and biocompatible polymer, which is approved by FDA, so it's safe to use. The very special advantage of PLJ is it does provide sustained release. So that's one of the importance, and they have different molecule weights and copolymer composition to to choose optimal formulation. And we often use nanoprecipitation method to make PLJ. This figure at the bottom just shows the very simple setup in our lab to make PLJ particles. Here is a study we did, a PLJ itraconazole nanospheres study. Itraconazole is antifungal agent. It had IV formulation called Spinarex, but it was later took off from the market because of renal toxicity due to its solubilizer, which is the cyclodextrin we mentioned earlier, because the concentration was too high. So we want to develop an advanced formulation for that, and so we studied different surfactant with different ratio. We studied the PLJ to itraconazole ratio and found the optimal one. We also studied different lyoprotectant, which is basically used during the freeze thaw to see which one will give the best particle after freeze thaw and lyophilize. And here shows some of the characteristics we obtained for the nanoparticles by different techniques. And we also develop bioanalytical method, HPLC, LCMS, MS method, and validate those methods, so we'll be able to quantify itraconazole at solution and biological samples. Finally, we did pharmacokinetic study with comparison to Spinarex at dose of 10 milligram per kg. Our nanospheres dose is half of that. Our studies show basically those two are bioequivalent. We can see an initial rapid decrease of the nanosphere formulation, but it's probably due to the RES uptake. The nanosphere provide a good sustained release up to 24 hours and improve the itraconazole bioavailability. So with all those basic information, I want to show a last example with a recent study we did on this compound C. I use ABCD, so to protect our users' information with their precious molecules. They probably haven't, gone in too far on the patent. So we look at this compound from very beginning to the end. We look at the compounds Lipinski rule. We can see they are pretty much satisfy the basic requirement for a potential drug. Here has some predictive value of their physical properties. As I said, the Pion instrument we just recently acquired, so we haven't get started to use them. With the new training going on like in 2 weeks, we will be able to provide more experiment data rather than just predicted data. Here's the solubility of the compound C in some of the excipients. As we can see, all the molecule we work with is either insoluble or very slightly soluble. So what we're trying to do is always increase the solubility. So they do have some good solubility as some of the solvents, excipients. So that lead to our current co-solvent formulation with drug solubility at 5 milligram per ml. That is with DMSO to water ratio 1:3 and stability over 24 hours. We include DMSO PEG 400, transcutaneous HPN saline. So this is a preliminary PK data we obtained from this formulation with 5 milligram per kg dose with 6 animals. And in addition to that, we have several self-microemulsifying drug delivery systems we are trying to develop with this under investigation for this compound. Specifically for this formulation 2, I want to mention it seems a very interesting formulation to go. They have the drug solubility to 5 milligram per ml. They have the size at 100. They are stable over 24 hours. This is how they look in the lab. So we're going to do more study on those preliminary formulation and see if we can also use them to further increase the formulation we have. We also did a preliminary study of PLGA loaded compound C. We do this PLGA formulation because we want to do dissolution study on PLGA nanoparticles. So this, I can mention earlier, this is SOTEX SUP apparatus 4 instrument, which is also a new industry standard instrument to do dissolution at nanoparticles. So this is some preliminary data. We just fresh out of my lab doing drug release, in vitro release at 2 different condition buffer, neutral buffer and acidic environment. So we consider we probably the first one doing PLGA study with this apparatus 4. So more study will be performed by changing the pH and also the composition of the PLGA. So here lists some of our previous existing users. Without them, we probably can never do those interesting study. I really appreciate them, and I welcome you to also trust us, give your precious compound to work with. And I want to thank our CPRIT grant support. Without the CPRIT grant, we probably cannot do most of the work almost free for those users. We have some members, either the faculty member and the staff member, as well as a previous account students. I really appreciate them. They are the one actually doing the work. And I thank you for coming, and I want to welcome you to visit TSU and also check our website at gcc-ccpf.com. Thank you very much.
For one of your advanced formulations you used, I think, are isopropanol as a stabilizer. Could you talk a bit more about that? Is it not toxic?
If we use any of those, we control the concentration to under the toxicity level. So we probably only use very few, but I cannot show the whole composition because they're under investigation. So if we use any of those solubilizer or surfactant or solvent, we have to control the concentration of that. Normally we look at the table to show what is the toxicity tolerance level. So we incorporate that into the consideration of the formulation.